let us come to our 35 lecture on transport phenomena, in which we will discuss this unsteady state heat transfer part 2, unsteady state heat transfer 2. In today's class, we will see that how this lumped heat capacity analysis can be used to determine the instantaneous flux which is subjected to heating or cooling. That means the body which is subjected to heating or cooling, then in that case how we can arrive at the instantaneous flux, as well as we will also see today that how the quantity of heat lost or heat gained by a body during the cooling or heating phenomena can be calculated using this lumped heat capacity analysis. After that, the most important thing in the unsteady state heat transfer is the unsteady state heat conduction in the case of semi-infinite solid will also be visited. Apart from that, we will also try to understand that what is the meaning of thermocouple and how the sensitivity of a thermocouple can be altered, how the response time and time constant of a thermocouple can be defined. Such a things of immense practical importance, as you might have gone through in the practical classes in the response of thermocouple, in which you have to calculate the response time of a thermocouple, you have to determine the time constant of a thermocouple against a unit step change in the temperature, and also you might have gone through the sensitivity of this thermocouple. All these things can be derived or can be understood by utilizing the lumped heat capacity analysis. So let us try to deal all these aspects in the today's class. So first is the expression for instantaneous heat flux. Instantaneous heat flux. So the instantaneous heat flux can be expressed as the instantaneous heat flux can be expressed as it is denoted by the letter Q suffix I. This is denoted as Qi is equal to rho CPV into the differential coefficient of temperature with respect to time, because of the fact that in the case of the unsteady state heat transfer, all the time the surface temperature of the body is changing and there is no heat gradient, there is no thermal gradient inside the body itself. Hence, in the lumped heat capacity analysis, we have assumed that there is no gradient existing within the body. So, the change in the internal energy which is happening in the inside a system or inside a body is equal to the heat lost by the convection through the ambient air. So, because of the fact that the dT by dt is not equal to 0 in the case of unsteady state heat transfer, that's why it is necessary and very, very important to evaluate this quantity for the present situation in order to arrive at the expression for instantaneous heat flux. Now, referring to the equation that I have derived in the previous class, so the expression for expression for T, that is the temperature, can be given as T minus Ti, T minus Ta, that is ambient temperature, divided by initial temperature minus ambient air temperature, that should be equal to exponential minus Ha upon rho Cpv into T. So, the expression for T comes here as T is equal to Ta plus Ti minus Ta exponential minus Ha upon rho Cpv into T. If you take the differential coefficient of this, you will arrive at dt upon dt, that should be called, this is constant, this quantity is also a constant quantity, so this will be Ti minus Ta, differential coefficient of this thing, so that will be minus Ha divided by rho Cpv, the constant, differential coefficient of T equal to 1, and differential coefficient of this, that will be exponential minus Ha divided by rho Cpv. Let it be question number 2. Let it be question number 1. Now, so the expression for the instantaneous heat plus Qi, that should be equal to rho Cpv into, put the expression for dt by dt from here, that is a Ti minus Ta into minus Ha divided by rho Cpv into exponential minus Ha by rho Cpv into T. So, this will get cancelled out, or you can say Qi divided by Ha, ambient air minus initial temperature Ti, that is equal to, because I have inserted the minus sign here, so that will be equal to that will be equal to exponential minus H into A divided by rho Cp V into T. So, the equation number 3 is the desired expression for the instantaneous heat flux assuming that lumped heat capacity analysis is applicable. So, mind it, this expression holds for the cases where it is being validated that the Biot number for that body is much lesser than 0.1. That means the size of the system is as small as possible, and also the convective heat transfer coefficient is much lesser than as compared to the thermal conductivity of the material from which that body has been made. So, this is the expression for the instantaneous heat flux. The second task is to determine or to evaluate the quantity of heat loss or gained by the body during a particular temperature T1 from initial to T1 or between the time interval T1 to T2 where T2 is greater than T1. So the next task is the expression for finding the heat lost or gained by the body during a time interval. So the next is the expression for heat lost or heat gained by the body during the time T1 from starting. Okay. So for this, let us suppose QL, I am assuming this is heat lost that can be quantified as the instantaneous heat plus QI into dt integration from 0 to t. This is the basic philosophy behind the calculation of the heat lost by the body during the time T1 from the starting. So 0 to T1. When you evaluate this expression, we will get an expression for quantity for heat lost. So what is the expression for QI from the previous one? So that will be equal to 0 to T1. Expression for QI, that will be taken as H into A into Ti minus Ta. So this will be minus sign. If you are using Ti first, then this will be minus exponential minus Ha divided by rho CpV into T. So that will be equal to minus H into A into Ti minus Ta. Integration of this is this much only, exponential this divided by rho CpV into T. Actually, this needs to be evaluated between the interval 0 to T1 divided by differential coefficient of this quantity, that will be equal to minus rho CpV divided by Ha. Okay. So it can be given as Ha, this will get cancelled out. So that will be equal to Ti minus Ta into rho CpV into exponential minus Ha divided by rho CpV into T1 minus exponential 0, that is equal to 1. So that equation can be further written as minus mCp. This and this quantity have been clubbed together. So minus mCp into Ti minus Ta and if you are putting minus sign here, then this expression will be 1 minus exponential minus HA divided by rho CPV into T1. If you further extend this equation in terms of the dimensionless number, then referring to the previous class, this quantity which is enclosed in the parenthesis associated with the exponential term can be represented as a product of the three dimensionless number, that is the Biot number, the dimensionless position, and the Fourier number. So this equation can be further written as, or we can write QL is equal to minus MCP into Ti minus Ta into 1 minus exponential. This is a product of three dimensionless number, that is the Biot number, into the dimensionless position G into Fourier number. This. In a similar manner, similarly, quantity of heat lost during a time interval from T1 to T2, where T2 is greater than T1, can be given as QL is equal to minus MCP Ti minus Ta into 1 minus exponential Biot number, dimensionless position, and Fourier number, corresponding to T1 minus T2. T2 is the upper limit. 1 minus exponential this. So, by the virtue of these expressions, you can easily evaluate the quantity of heat lost by the body during a particular time interval T1 to T2. Now come to the next part of the today's class is the important parameters regarding the thermocouple temperature measurement. I am giving you some important definitions parameters for thermocouple temperature measurement or temperature measurement through thermocouple. first important quantity is response of thermocouple. Please put emphasis on these things because these are very, very important. So far your practical viva voce examination with respect to practical TP practical is concerned. At the time of examination we will be conducted a viva voce in which such type of questions may go. The response of the thermocouple response is defined as the time required or the thermocouple to reach to source temperature. Now, referring to the equation for the unsteady state heat, T minus Ta divided by Ti minus Ta, that should be equal to exponential minus Ha divided by rho Cpv. If I am saying that the thermocouple is reaching the temperature of the source, it means tends to Ta, that the temperature of the ambient air. So, if I am putting this limiting case here, so it means this quantity T minus Ta divided by Ti minus Ta, if T is tending towards Ta, then it must tend towards 0. It means x minus quantity, this must tend to 0. What does it mean? It means it is tending towards 0, then it is possible that the E infinity, e to the power minus infinity, that means this term must tend towards infinity. This term must tend towards infinity because e to the power minus infinity, that is equal to e to the power infinity, that will definitely tend towards 0. Minus Ha divided by rho Cpv into T, that must tend towards 0. So this can be made possible. This can be made possible either through increasing the convective heat transfer coefficient, either through increasing the convective heat transfer coefficient H, or so increasing the value of convective heat transfer coefficient, it means you have to change the ambient atmosphere. Many times it may not be a practical situation that every time the convective heat transfer cannot be changed as per the demand of the situation. So for an engineer, what should be the second methodology, what should be the second thought which can be implemented on a practical ground is the most important thing. So to investigate that which is the next practical term, so this quantity A by V. So let us suppose A So its area which is through heat transfer is being carried out is 2 pi Rs, that is the curved area, divided by volume is the pi d square h. So h pi, this will get cancelled out, that is equal to pi r square h. So that will be equal to r, that means equal to 4 upon d. It means this quantity A by V will increase. This quantity A by V will increase if I am reducing the thermocouple. This is the important design aspect of this thermocouple. The diameter of the thermocouple should be as small as possible. Henceforth, you can easily see that whether the copper constantan or platinum rhodium or iridium platinum, whatever the metal combination may be, the diameter is kept as a bare minimum. Why? In order to increase the response time. Once you have put up the thermocouple in the atmosphere, you can easily judge the temperature, what is the temperature of the atmosphere in a quick succession of time. So rather than increasing or decreasing the value of the convective heat transfer coefficient, it is more near the diameter, so that this quantity 4 by d can be maximized as per the demand of the situation. So the second methodology is through increasing the convective heat transfer coefficient or decreasing the diameter of thermocouple. Decreasing the first variable, that is the response of thermocouple. The another quantity which is the sensitivity of thermocouple. The next quantity is parameter sensitivity of thermocouple. Next quantity is sensitivity of thermocouple. So B thermocouple. This is defined as the time required by the thermocouple to reach (63.2%) of the value of initial temperature difference. Initial temperature difference. Initial temperature difference means Ti minus Ta. Initial temperature difference. So this is what is your sensitivity of thermocouple. Time constant. Time constant. Time constant. This is abbreviated as later. It is time required by the for temperature change to 8% of its final value response to a unit response to a step change in temperature. My go through the definition, try to understand what is the meaning of this type of definition, and try to get by heart practical viable exam. So the next thing is the unsteady state heat conduction in the case of semi-infinite. Is unsteady state heat conduction in semi-infinite solid. Heat in semi-infinite solid. A semi-infinite means that one of the dimension is not finite in nature. If one of the dimension of a body is not finite in nature, then it is called semi-infinite. So, of a meaning of the infinite rod is its diameter is fixed but the length is infinite. So, let us consider one end of a semi-infinite rod along which temperature is constant temperature T naught. So, for the present case, the initial condition can be represented as at time t is equal to 0 and x greater than or equal to 0, and the boundary condition is, this is the initial condition, and the boundary condition should be how much? The boundary condition is equal to T naught, T is equal to T naught at time t greater than 0, x is equal to 0. So, because the unsteady, so the differential equation controlling differential equation for the present case, differential equation for the present case should be what? This should be equation number. Equation number 1, partial differential equation. Variables are involved here, t and x. This is a partial differential equation which involves two parameters, t and capital T and x. Small are the two variables associated with this partial differential equation can be converted. So this is partial differential equation. Use the abbreviation in the case of mathematics. So the equation can be converted into an ordinary differential equation by inserting a term or by using a term eta equal to 1 upon eta equal to x upon 2 under root alpha t. Alpha thermal diffusivity. Alpha is the thermal diffusivity. Once you are utilizing this term eta is equal to 1 x upon 2 root alpha t, if you visualize that, if you can examine the nature of this term x is equal to x divided by 2 under root alpha t, you will find that this quantity is entirely dimensionless in nature. Let us see how. Dimension of x is L divided by under root alpha has the dimension L square t raised to the power minus 1 into t. That means L upon L, that is equal to 1. So this quantity is dimensionless in nature. So eta is a dimensionless quantity. So let it be question number 2. And the solution of the equation number 1 of eta is given as solution of differential equation 1 is given as t minus t naught divided by ti minus t naught to error function x divided by 2 under root alpha t. This error function eta or error function x divided by 2 under root alpha t is defined as this quantity error function, that is a case of a special function in mathematics. This is defined as 2 by under root pi integration from 0 to x divided by 2 under root alpha t square this quantity minus x square by 4 alpha t dt. This is the solution of the differential equation as encountered in the case of the heat transfer in the case of a semi-infinite solid. So So rewriting that that is equal to 2 by root pi integration 0 to x divided by 2 under root alpha t exponential minus x square by 4 alpha t dt. So from this expression, the value of dt upon dx, that should be equal to ti minus t naught into differentiation of this quantity, considering integration is a reverse process of differentiation and vice versa. Quantity the differential coefficient for this part may be given as 2 by root pi, this is a constant quantity, differential quantity exponential minus this quantity square. So that differentiation will be 2 into this or into half, that is equal to I into this exponential minus x square divided by 4 alpha t. So this 2 will get cancelled out, this will cancel out, so that will be equal to ti minus t naught into 1 upon under root pi alpha t into exponential minus x square by 4 alpha t. So this is the value of dt by dx that we have obtained. Now keep this intact to proceed further. So evaluate this quantity at x is equal to 0 now in order to determine the heat flux. So the value dt upon dx at x is equal to 0, that should be equal to ti minus t naught into 1 upon pi alpha t, and this is value 1. So the heat flux, that is q at x is equal to 0, that should be equal to minus ka dt upon dx at x is equal to 0. So quantity, if you put the value for this quantity, then it can be given as ka t naught minus ti divided by under root pi alpha t. So this is the expression for heat flux. At the beginning of the class, I have derived the expression for the heat flux and the quantity of heat loss during a particular time interval if the lumped heat capacity analysis is being used. Now in the case of semi-infinite solid, the total heat lost that can be quantified as equal to q x equal to 0 into dt from the time 0 to t. So that will be given as ka t naught minus ti divided by under root pi alpha integration 0 to t to the power minus half dt. So that will come as 2 ka t naught minus ti divided by under root pi alpha into T raised to the power half. This expression, such type of expression is of immense importance again for your practical classes, such as you might have gone through the experiment number 7, that is the ladle cooling, in which we determine the quantity of heat particular time interval from a ladle which is containing hot liquid or hot metal. Hot metal can be is replaced in the lab scale by the hot water. So this formula can be used at those places. So this is also very, very important for your viva voce exams. In the next class, we will see the unsteady state heat conduction taking place if we are subjecting any metallic plate for quenching, and that metallic plate has finite thermal resistance. Till now, we have dealt with the cases in which there is no internal resistance. That is, the lumped heat capacity analysis is being applicable in those cases. Now we will consider the case where the system or body has finite thermal resistance. Thank you.